Hello, my little scientists. How are we? Good evening. Welcome to another session of STEM at Home. This is our last session, 103, and we are covering water everywhere. Abby is here. Hello, Abigail. So, you need to have a big flat baking dish. Could be glass, could be metal, could be plastic. We want to fill that with water, not up to the tippy top because we don't want any spillage, no accidents. It just needs to be a little deep. We want to be able to float something on the top of the water and not have it reach the bottom. What else do you need? You need some liquid dish soap and some coloring utensils. And I think that's it. I think everything else is in your kit. So let's talk about our kit. This is what you have, what you came and picked up. So let's take all of the items out. I gave you some bookmarks. This is from a STEM organization in our area who gave me all of these to share with you. And they're all different. And some of them have like little activities to do on the back. Some of them are just promoting STEM jobs because let me tell you, kids, when you're ready to enter the workforce, their jobs are going to be all about science, technology, engineering, or math. That's why you hear so much about this STEM. So take a look at those bookmarks. You have a QR code that you can scan, and it probably takes you, yes, it does, takes you right to their website. They give you some really fun science things to do on that website as well. You have a, let's start with our first project. In your kit, you have these two like pedal looking things. That's going to be for our first project. Then you have a cardboard monster. He's our water beastie. We're going to decorate him. That's for our second experiment. And then we have a fish and a toothpick. And that is going to be for our third activity. Okay, oops, my beastie fell on the floor. So this, as I said, is 103. If you missed 101 and 102, the videos are still on our Facebook page and on our YouTube channel, so you can go back and watch them if you'd like. I'm going to point the camera down. Let me make some room here. All my things. I'm going to put stuff in reaching areas. Okay, so camera down so you can see my table. There we go. All right, here is my dish of water coming out. All right, I'm going to leave that back there just for a second so that I can talk to you about the scientific method. Now, is that backwards for you? No, I don't think it is. Okay, so what is the scientific method? Well, it's a procedure. It's a series of steps that is considered very necessary for scientific investigation, for experiments. And it has some basic parts. It starts with a question, and then it moves to an hypothesis, then experimentation, then observation, then the data, and then the conclusion. So all experiments, all activities start with the question, what would happen if, or does this work? And your educated guess, without really having any kind of information, is going to be your hypothesis. You say, I think this is going to happen, before you do any kind of experiment. So then you conduct the experiment, right? And you observe what happens. You measure the results, analyze the data, you compare it to your hypothesis. Did the data show that what you thought happened really happened, or was it different? Was your hypothesis correct, or was your hypothesis wrong? And then that brings you to your conclusion, is your new answer to the question that you posed. And the conclusion is now based on all of the information that you gathered when you did your science experiment and went through the scientific method. Okay, so that's your basis of all science experiments. Now, our first scientific experiment demonstration is called blooming flowers. I went ahead and cut these flowers for you. Now, I know it looks kind of more like an X than a flower. But each flower can only be used once. So if you want to make more, I did do two kinds. And I'll talk a little bit about why. If you want to make more, all you do is take a piece of paper, fold it in half, then fold it in half again, and you draw a petal shape coming out of the corner where all the folds are. There's folds here, folds here. Draw a petal shape, cut it out between all the layers, or cut out all the layers all at once, I should say. And then you'll have your flower shape. You could do different shapes too. I did really long pointy ones. You could do more rounded ones, and we'll talk about that too. Okay, so the first thing that we want to do is fold in the tips. I'm going to take each petal and I'm going to fold the tip into the center. And I'm going to crease it really good. There's 1 and 2 and 3 and 4. And what we want to do is make this flower bloom. So in nature, what does it mean when a flower blooms? Usually the bud is really tightly closed together, and as it blooms, it slowly starts to open, right? So this experiment is called blooming flowers. We're going to make this flower bloom. Now all we have to do is place this folded flower onto the surface of the water. And we are just going to observe what happens. Okay, so I am just going to, whoa, look at how fast that went. It bloomed. Isn't that cool? And then, yep, it soaks up all of the water and it's done blooming. Okay, so I'm going to pull that out, shake off the excess, and I'm just going to put it aside. Like I said, we can only do it once. You could let it dry, refold it, and then do it again. But, you know, if you want to do it like immediately, you could only do it once. But that's why we have a second. But did you notice that the second is not only a different color, it's a different color. It's still construction paper, but it's a different color. The reason why I did that is because of this thing called variables. So variables are things that could change in your scientific method that will cause you to perform a similar experiment, but with something changed. Now, you only want to change one thing at a time when you are performing an experiment. So in this experiment, we are changing the type of paper. So we're going to see what happens with this paper as compared to the first paper that we used. So again, we're going to open it up and fold all of the tips into the center. And we're going to see, does it open just as fast? Does it open slower or faster? All right, I'm going to drop it in and watch what happens. It seems to be going slower. There you go, mine's slowly opening. So what is the difference? Why is this one slower than the other one? Well, what I could tell you is paper is super absorbent, which means that water can soak into it. So as the flower is absorbing the water, the tiny strands that make up the paper swell. It's like, did you ever take a dry sponge and put it in the water? It might be really tiny and shriveled, but once it fills with water, it gets really big, right? It swells up. So it pushes the tips out and causes it to bloom. Now, if the flower is made from a very absorbent paper, like the red one, it's going to open very quick. But thicker paper or less absorbent paper is going to open more slowly. It's going to take more time for all of that water to absorb. This one got in the way of my edge. Let's see. There we go. Now it's opening all the way. So you can test this out with all kinds of paper. Lined paper, really heavy cardstock, tissue paper. That's very lightweight. I bet you that that would absorb the water very fast. But remember, you only want to change one thing at a time. So now we're changing the paper. Maybe instead of changing the paper, you could change the size. So take the same paper, but make bigger flowers and then do the experiment again and see if that makes a difference. Bigger flower means it has to absorb more water before it opens, right? So maybe it wouldn't open as fast. Another force that is working here is called capillary action, and that is the ability for liquids to flow without gravity or opposite gravity. So when the petals started to open, the water was actually flowing up, right, to the tip. It wasn't flowing down like we know water does down rivers and streams and waterfalls and things like that. Instead, it was flowing against gravity or without the assistance of gravity. Okay, so the next one that we are going to do is our water beastie. So we're going to decorate him a little bit first, shall we? I have some markers, some coloring utensils here, and I just want to give my guy an eyes and a mouth. I want to give him a smile with a toothy grin, because he's like a monster, kind of. And I'm going to give him black eyes. And maybe he's got a spot around this eye. Now this is just cardboard from cereal boxes and cracker boxes. I think I used purple instead of black. I don't know. There we go. This is black. Alright, so he's got a little eye and some tooths. And what if I gave him some polka dots? We're not going to spend too much time on this because it is not an integral part of the experiment. What does that mean? It's not a very important part of the experiment. I just like to decorate. He's got these like spikes on his back. All right, and then I'm just gonna color in his spikes. There we go. Okay, so my water beastie is decorated. Now, we want to fix his feet. We're going to fold out his feet. Let's see. I want to make sure you can see everything. Okay, so what we're going to do, how we're going to fold his feet, we're going to take them and flip them up so that he can like stand flat. So the ones in the front, we're going to flip up, and the ones in the back, we're going to flip back. So let me show you. You're going to crease it right at his ankle, right where his foot begins. So I'm going to flip the front ones up and then flip it over. And I'm going to flip the back ones back. So that, look at, he could stand. Right? He's got feet. Hey, look. Oh, look. Frosted shredded wheat. That's what this one came from. It was a cereal box. Frosted shredded wheat. Okay, so he could stand. Right? Now, can he stand on water? Can you stand on water? I can't stand on water. Can he stand on water? Let's try it out. We're going to put him on the water. Let's see. I'm going to very gently set him down. He sank. You know what? Maybe the cardboard is too thick. Now, see, the first time I did this, he floated. That's what's supposed to happen. But, you know, like in life, things don't always go according to plan. Sometimes what you think is going to happen or what's supposed to happen doesn't happen. And then what? You try again. Yes. Or you try something else. So we only have one water beastie, right? So we can't try again with him. But we could try our fish experiment because he's going to lay on the water. And I can explain to you why he would float normally. Maybe his feet are not big enough. You need a big surface, like our petals, right? Our flower was pretty big to float on the water. His feet, maybe I made his feet too small this time. I thought I copied my template though. So the reason that the petals floated on the water, which is why the beastie was supposed to float on the water, was because the surface of the water is like a very thin skin. And the petals, and then you'll see also with the fish, it spreads its weight over the top of this skin and floats. Now, the variable you could change would be the size of the feet. So, okay, so this experiment we know small feet doesn't work. It would break through the water surface. Or pointy feet would probably break through the surface of the water. But maybe bigger feet. We need big feet like the petal. Big, giant feet. Maybe that would make him stand up. That's the purpose of the scientific method, doing the experiment again, changing only one thing, the size of the feet. We could change what Beastie is made out of. Maybe if we used regular paper instead of cardboard, maybe he would float better with smaller feet and wouldn't need the bigger feet. That's the purpose of experimentation. Okay, so we'll put him aside. That was a failed attempt. But we've got one more to try. And this one I think you're really going to like. Now, this is also something that you can only do once. To do this more than once, you have to throw all your water out. You have to rinse and dry your dish and then fill it back up with new water. So we can only do this experiment once. I am going to add a little eye and fin to my fish to give him some personality. Uh-oh, sounds like we got some weather coming. That was my weather alert. Okay, what kind of fin am I going to give him? Just a little loop-de-loop. Okay, so let me explain to you what we're going to do before we actually do it, since it's so important that we do it correctly. Otherwise, we have to throw all the water out and start over. Here's what we're going to do. We're going to use the toothpick to put a small blob of dish soap right in the V of the tail. Right in there. So we'll put some dish soap on the tip of our toothpick and then put it on the tail in the V. Then what we're going to do is we're going to hold our fish flat like we did our petals, and we're going to drop the fish into the water. But we want to make sure that the fish tail is like close to the end of the dish and that he has lots of room to go for a swim if he would like to do so. Okay, so that's what we're going to do. I'm going to get my soap, and I actually am just going to stick my toothpick right in there. And I'm going to scrape the soap onto the fin, right in the V. See if I could show that to you. That's the back. That's the front. I feel like maybe it needs a little bit more. Let's do a little bit more. I want to make sure I get a nice blob on there. I want a good result. Oh, here's what I'm doing. Sorry, it was off camera. All right, so now I got a blob of soap. Okay, and I'm going to hold my fish flat and drop them. Whee! Did you see that? Now see, even if I try to turn him around, he moves just a little bit. There's still some little bit of soap left in there. He's swimming back to the other side. Did it work for you? I hope it did. So why did my fish made out of paper suddenly decide he wanted to go for a swim? Well, remember that skin on the surface of the water that we talked about? It's held together by a thing called surface tension. Now, the soap on the fish, when it touches the water, it leaves like this film, and the soap pushes the skin that's on the water away from it. The soap is like, get away from me. So because The soap is pushing the water away. That pushes the fish in the opposite direction. And that propels the fish forward. So, when I first put him in like this, the soap that was here was pushing the skin of the water this way and caused the fish to swim this way. Now, when I tried to turn him around, that's because there was still some soap left on the fish, but no soapy film on the skin over here, or not a lot anyway, so he was still able to move forward a little bit. But now my fish is sinking, and the surface of the water is now contaminated with soap. Sometimes you can see it. If you look sideways, when the light hits the surface of the water just right, you might be able to see some swirling colors. You can see the soap on the film, or on the surface of the water. So that's why now, to repeat this, we've got to throw out the water. We've got to rinse it out, dry it. We have to make sure that there's no soap left in this container at all, so that we could do it again. Put more soap on the fish, drop them, and then that soap will push the skin away and push the fish forward. And there you have it. That is STEM at Home 103, our final session, which is also in Science September. That is a real thing. It's a hashtag. You could look it up. And people are doing all kinds of science things this September. Thank you for joining me. Check out the rest of our events that we have going on for September and October. We have some fun things, and I hope to see you again real soon. Bye.